Okay. Well, thanks for being here. Hopefully, I can help get you ready for the final. The plan is, if we can, maybe get through thermo and most of kinetics tonight. Start with the old stuff first, because that's probably the stuff you need to refresh more. Okay? So that's what we'll do. Today, this morning, I posted this study guide in Blackboard. Along with 2 practice finals. Okay? Along with answer keys to all that as well. So this list, by each chapter, those are the things that you should know from each chapter, and then how many questions on the final that will come from that material. That's pretty nice, huh? So from the thermo chapter, there will be 6 questions. And it will pretty much follow order from starting with thermo, going to the end of the semester as you're working the final. Okay? All right. So hopefully this will work. I'm trying to record this as well, so I have 2 microphones going here. We'll see. Yeah, feel like I'm ready to go. Okay. So I thought, and let me know if you think that we should do something different, but I thought I would go through each of these bullet points and just kind of explain them a little bit, and then if there's any questions on those, we can work an example problem or something like that. Okay? We could even go to a problem on the practice final if anybody's looked at those yet. All right, so let's just start with the, yes?
I can't find the final, anything on Google Learn. Where is it at?
It's in the exam review folder. Is it there? There's no folder in the exam review that says final exam? No. Danielle says there is. Did I not put it in? Maybe I just put it in one section and forgot the other one?
I'm not seeing it either.
Okay. All right. Sorry. I probably thought I put it in both sections, but maybe I only put it in one. So, what's that? Danielle, what section are you in? 3. So you're in section 2? Gosh darn it. All right. I'm sorry. I will do that when I get home. I thought I uploaded to both sections. All right. So if you're in section 2, this will be there, plus practice finals. So the first thing on this list, know the sign convention for delta S. Does everybody know the sign convention for delta S? So an increase in entropy. Okay, Oh my gosh. Let's try this again. Increase in entropy. So more, which we could describe as more disorder or a greater dispersal of energy. What sign is that? Increase in entropy. That is positive. Okay? And that makes sense. It's an increase in entropy. Processes will tend to go to increased entropy, more energy dispersal. Okay, more disorder. So then a decrease in entropy would be negative. Okay? Let me just double check that. All right, this says it's recording. All right. Next one. Qualitatively identify whether entropy increases or decreases for a reaction. Okay, so this is just looking at a reaction and looking at your reactants, looking at your products, and then saying, is delta S positive, is delta S negative for that reaction? Okay? So, you might have something like, so what do you think about that? Is that an increase or a decrease in entropy? That is a decrease. Okay, we're going from 4 moles of gas to 2 moles of gas. So the number of particles of gas that are moving around has been cut in half. Okay, so energy is going to be less dispersed in that fewer particles of gas. Okay, so a lot of times you can look just at the amount of gas that's present on each side, because gases are more disordered than liquids, which are more disordered than solids. Okay, don't forget about solutions. So if we took something like sodium chloride dissolving in water, what is delta S for that? That is an increase in entropy. So we're taking a highly ordered ionic solid. We're taking water, which has some order for a liquid due to the hydrogen bonding. And now we're separating those ions, surrounding them by water, and those ions are moving through that solution. So this is an increase in energy dispersal, an increase in entropy. Okay? So there's no calculation there. It's just look at a reaction, look at both sides, and figure out, based on what phase you have, how many moles of each thing you have, and whatnot, whether it's increased or decreased. The next one is also qualitative, predicting which substance has the greatest entropy. Okay, so example, if we looked at oxygen gas versus chlorine gas, which has the greatest entropy? Or the greater in this case, since there's only 2. Yeah, it's based on size. Okay, so the larger, so if they're both, in this case, they're both the same phase. So sometimes you're going to have to look at the phase. Of course, gases are more disordered than liquids, which are more disordered than solids. So you would look at the phase. But if they're in the same phase like this, you're going to look at the size of the molecule. Okay, larger molecules, a lot of times, this one does not, but larger molecules will tend to have more bonds, which stretch and bend and do other things. There will be more electrons in motion. Okay, energy will be dispersed through that motion of the electrons and so on. So we typically just look at size. And molar mass is a good predictor. So this would have the greater entropy. Okay, the chlorine gas compared to the oxygen. Any questions so far on entropy? This is just qualitative stuff with entropy. Sign convention, predicting delta S increase or decrease for a reaction, just looking at a couple of molecules and figuring out which has the higher entropy based on phase and size of the molecule. Good with that? All right, endothermic and exothermic, and know the sign conventions. So what does endothermic mean? Okay, so an endothermic reaction absorbs heat. Okay, or we could say heat is transferred from where to where? Surroundings to the system. Oops, I lost an S there. Transferred. Okay. So an endothermic reaction is going to absorb heat from the surroundings. Okay. Exo, then, you probably know, those release heat. Or we can also talk about transfer of thermal energy, transfer of heat. So from the system, in this case, out to the surroundings. Okay, so know those definitions. That's just helpful when you're given, enthalpy change and knowing what's going on. The sign convention, you need to know that as well. So endothermic, delta H is what? Positive, absorbs heat. Exothermic, you can think of it as the reaction or the system is giving heat away. Okay, the metathermal energy of that system is decreasing. It's going out to the surroundings. Good with that? All right, next one. Delta H and delta S predict spontaneity based on the signs of delta H and delta S. Everybody loves this. There's 4 possibilities. Okay, and this is why it's important to know the sign conventions. So you know if you just have a negative delta H and a positive delta S, what does that tell you? So look at the first situation. What does that tell us?
It's spontaneous at higher temperature.
Mm-hmm. So delta H negative means what? Exo. Delta S positive, increase in entropy. Both of those are favorable. Okay, remember. Yeah, so this one is always spontaneous at all temps. Okay, so I like to think of it in terms of favorability. Reactions that release heat tend to be spontaneous, and reactions that lead to an increase in entropy tend to be spontaneous. So if you put those two favorable quantities together, this reaction will be spontaneous. And we might as well do delta G here while we're at it. So what would delta G be for this first situation, negative and positive? Delta G will be negative. So again, there's another sign convention. We talked about this one recently in class because we went back and looked at delta G and the cell potential and the equilibrium constant. But a negative delta G indicates that the reaction is spontaneous. All right, what about the opposite situation, endothermic and a decrease in entropy? Not spontaneous. And again, we're looking at the forward direction. Okay, reactants to product. So that would not be spontaneous in the forward direction. It would be spontaneous in the reverse direction. Okay. So what would your delta G be for that one? It would be positive. Okay, not spontaneous. And situations 3 and 4, what can you say about those just in general? They will be temperature dependent. So in both those cases, positive, positive, negative, negative, we have one favorable quantity and one unfavorable quantity, and it will depend on temperature. So both of these, oh, that was not what I wanted. So temperature dependent. So what about the first one, positive and positive? If it's not spontaneous, it will become spontaneous as you do what to the temperature? Increase the temperature. Increase. This is endothermic. So the way I just like to look at the heat flow for these. Endothermic reactions need to absorb heat. So if it's not spontaneous, you need to put more thermal energy into that system, more heat in that system. So this first situation, increase temperature if it's not spontaneous. And the second situation is going to be the opposite. Exothermic, we need to get heat out of the system to the surroundings. And we can help heat flow out of the system by lowering the temperature of the surroundings. Okay, so if we decrease the temperature of the surroundings, heat will more likely flow from the hotter system to the cooler surroundings. Okay. You'll hear these described that the first situation, positive, positive, is spontaneous at higher temperatures, and the negative, negative is spontaneous at lower temperatures. That's not quite correct. I would rather you think of it as, well, if it's not spontaneous, what should you do? Okay, so the positive, positive one, if it's not spontaneous, you should raise the temperature. The negative, negative situation, if it's not spontaneous, you should lower the temperature. Okay? So you guys remember this, right? Okay. Any questions on that? So you can see there's quite a bit of qualitative stuff you need to know from this chapter. We haven't done any calculations really yet, but there will be calculations. We good? Stop me at any point if you want things clarified. All right, next one. Here's a calculation. Calculate the temperature at which a non-spontaneous reaction becomes spontaneous. So we just talked about the two temperature-dependent situations. How would we calculate that temperature? What would we do? Flip a coin? Yes, Jeremy? Well, calculation for a phase change is similar. We make the same assumption about something in this equation. So this is definitely an equation you should know. So there were two situations where we made the same assumption using this equation. Temperature at which a reaction becomes spontaneous, or sometimes we would calculate, say, the entropy change of a phase change. And what assumption was that? Reach way back in there somewhere. Delta G is what? 0. Delta G is 0. Okay? So for spontaneous, we really want to find out when delta G is negative. But 0 is right on that dividing line between positive and negative. So if we, in this case, set delta G equal to 0, we can then rearrange this equation and solve for temperature. Okay, so if you remember to set delta G equal to 0, this becomes a pretty darn easy calculation, except for one other thing you have to consider. What about your units for this one? What's that? I can't see who's speaking right now. Who's talking? Oh. We have to convert delta. Yeah, you either have to convert delta H to joules or delta S to kilojoules, because your delta H most likely will be in kilojoules. That's the common unit for delta H. And your delta S will most likely be in joules per Kelvin. Okay? So in general in this chapter, watch for units. Okay? Delta S is in joules per Kelvin, almost always. Delta H is in kilojoules. Delta G is in kilojoules. So you need to watch for that. Okay? Even if you use this equation here straight up, you know, your delta H would be in kilojoules, your delta S would be in joules per Kelvin. You okay with that? All right. Next one. Make sure you can calculate delta G, delta H, or delta S by summing together, and I just put the values of the products, but it depends on what we're solving for, and subtracting off the values of the reactants. Does everybody know what I mean by that? Okay. So for all of these, This is an old computer, and there's lots of stuff going on right now. So I might have to save this and then reopen the blank file at some point. All right, but you should be familiar with, we want to calculate delta S for a reaction. Now remember, reaction and system are used interchangeably. So when I say reaction, I also mean system. I'm going to be sad when I have to get a new computer. Had this one for 8 years. Can you believe it? Wow. Scary. All right. And it still kind of works. Go figure. All right. Does that look familiar? You know what N stands for? Moles. So the coefficients from the balanced equation. So don't forget that. All of these are the standard entropy values. These are all per 1 mole of substance. Okay. The equations for delta H and delta G look very similar. And I'm not going to write I'll write one more, but you get the idea. Okay. Now those equations will be on the equation sheet. I apologize to section 2. The equation sheet is not there for you yet. If you're in section 3, you can look and see what the equation sheet's going to look like for the exam. But I promise tonight I will get section 2 caught up. And it's unfortunate because section 2 goes first, right? Yeah, section 2 goes on Tuesday and section 3 doesn't go till Thursday for the final. So, oh well, I'm sorry. I'll make it up to you somehow. All right, one other thing to keep in mind here. Those, yes.
I don't know if I'm excited or nervous.
Delta H of formation and delta G of formation for an element in its standard state. I see Jeremy going like this. It is 0. Okay. Now by standard state, this is the standard state at, and we should probably say 25 Celsius. Okay. So that means the phase of the substance, and then also, for example, a lot of the elements are, say, diatomic. So the standard state of oxygen at 25 Celsius would be O2 gas. Okay? Hydrogen would be H2 gas. Okay? Most of the, pretty much all the solids, they're just going to be, sodium metal, potassium metal, titanium metal. Okay? But when you get to the nonmetals, a lot of those hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine are diatomic. Okay? All right, so keep that in mind. You might see that. Everybody's okay with this calculation? Do we need to do an example? Everybody's done plenty of these? Yes, Ariel?
Is each of them 0, or does it just equal 0 for the HM?
Well, if it's for an element, whether it's delta H of formation or delta G of formation, if it's for an element, say O2 gas, delta H of formation would be 0, and also delta G of formation would be 0 for that element. Okay? Now, standard entropy values, that does not come into play because everything is going to have an entropy value. Okay? As long as it's above absolute 0. All right, I think we kind of already looked at this next one. Calculate delta G from delta H and delta S. That equation will be on the equation sheet. You probably know it. Again, we talked about the units. Watch your units. Delta H in kilojoules. delta S in joules per Kelvin, so you're going to have to convert one or the other. Most likely the joules, because if you're solving for delta G, you're going to want to express that in kilojoules. And what about temperature? Yeah, temperature certainly needs to be in Kelvin. Okay. So this type of problem, if it's on the final, is really just plug and chug, which is kind of nice, but just be careful with units as you do that calculation. And I think we already did the sign convention. We didn't quite mention equilibrium, so let's do that. So we did the sign convention. But what will that mean once that system reaches equilibrium? In terms of the equilibrium position, is that product favored or reactant favored? Product favored. Okay? So if it's spontaneous, when that system reaches equilibrium, we're going to have a lot more products. So this, we could also describe this in terms of equilibrium. This is a product favored reaction. They go together, but it's a little bit different in terms of equilibrium. We haven't got to equilibrium yet, but that would be a large K, mostly products at equilibrium. Okay. Opposite, positive. All right. Any questions on thermo stuff? Doesn't seem like we did this that long ago. Yes, it does. All right. But it's good to start with this because I think it's better to start with the older material, spend a little bit more time with that. Particularly if you took the retest last night, you should be pretty familiar with all the acid-base stuff, the buffers, the titrations, and so on. All right. Should we go to kinetics? Yes? Sure, why not? Why not? Is there anything better to do? I mean, come on. Where would you rather be? All right. Common units of reaction rate. Common units of reaction rate. So by definition, rate is change in concentration over change in time. So what are your typical units of rate? Molarity. Molarity per second. Now, it doesn't have to be molarity, but that's the most common concentration unit in chemistry. And it doesn't have to be a second, but it has to be some unit of time. And that unit of time will vary depending on how fast or slow the reaction is. If it's a really slow reaction, you might be talking, your time might be in years. If it's a really fast reaction, your time might be in nanoseconds. Okay, it just depends on the reaction. Okay, so know those units. If you are given a rate, determine the rate in terms of another reactant or product in the reaction. Does everybody know what I mean by that? Not really? So we're given the rate at which hydrogen is reacting, 0.06 molar per second. At what rate is ammonia being produced? So what do we do with that? Dun, dun, dun. Time's up. Everybody's just looking at me. What's that? It's related to the number of moles, exactly right. So the mole ratio, you're going to need the mole ratio. Or you need a new computer, one of the two. So it is related to the mole ratio. What I would recommend is changing your molarity to moles per liter. So that's the rate for hydrogen. So I would write that as 0.06 moles of hydrogen per liter. Right? Molarity is just moles per liter. And then we still have seconds there as well. And we want to get to the rate for ammonia. So that will be moles of ammonia per liter per second. Okay? So we have to go from moles of one thing to moles of something else. Yeah, no, not molar mass, mole ratio. Okay, moles to moles, it's stoichiometry, it's mole ratio. So all you have to do is look at your coefficients. We want to get to moles of ammonia. We want moles of hydrogen to cancel. And then just write in your numbers, 2 for ammonia and 3 for hydrogen. I think that just comes out to 0.04, right? 0.04. Okay. So the rate for ammonia should be slower because for every 3 hydrogens that react, we only form 2 ammonias. So it's going to be formed at a slower rate compared to hydrogen reacting. You okay with that? Okay. I think that one's pretty self-explanatory, but what the A and B mean is a reaction that is A plus B going to products. Okay. So for the rate law, rate will always equal to a rate constant, and that's the lowercase k, and then the concentration of each reactant raised to some power. Okay? And remember, in general, we cannot get those exponents from the balanced equation. We have to solve for those. So the x and y in this equation, we're going to have to solve for those. Question? No? And I kind of wrote over that, so let me get those circles out of the way. Okay, so that's the general form of the rate law. We'll always take that form. Each reactant raised to some power. All right. The rate constant is a constant. Okay, at a given temperature for that reaction. Okay, and we'll see that when we do a calculation. I'm guessing you'll probably want me to do a calculation for rate law, to solve for rate law. All right, next one. If we change the concentration, know how the rate will change based on the exponents. Okay, so as an example, let's say we have a rate law that looks like this. Okay. We double the concentration of A, and we triple the concentration of B. If we have that rate law, by what factor will the rate change? Simple? What do we do with that one? You can just plug in the numbers. So really what you're doing is you're solving for the rate when the concentrations are 1 molar. And then if we double the concentration, it's now 2 molar. And if we triple the concentration, it would now be 3 molar. But we can shortcut it and then just say, well, we're going to double that one. We're going to triple B. So 2 squared times 3, 4 times 3. Our rate will go up by a factor of 12. Okay, and that's compared to whatever it was. So whatever the rate was, after we make these changes, the rate will be 12 times faster. Okay? All right, next one. Solve for a rate law given a table of concentrations and rates. Do we need to see this? I would assume yes. All right. Let me find a problem. Okay, I know there's got to be a problem here somewhere. All right, here we go. Let's write some numbers down here. Oops. All right, so there's a table of data for 3 separate experiments. Okay, so make sure when you look at this, you see 3 separate experiments. We run the first experiment with the concentrations of 0.005 and 0.002, okay, and then we measure the rate. We then change the concentrations and then measure a new rate. And then the third experiment is another set of concentrations. This reaction is obviously NO. Let's see, let's write, I guess we should put the reaction here. Okay, so there's the reaction. Okay, and remember, typically you cannot just look at the coefficients of 2 and then say, oh, these must both be second order. Okay, so we're going to have to solve for that. But we do know, since these are our two reactants, that the rate law will take this form. Okay, so it will be rate will equal a rate constant, concentration of NO raised to some power, concentration of H2 raised to some power. All right, so let's say we want to solve for the order for NO. What experiment should we look at? 1 and 2. Okay, so if we want to know how nitrogen monoxide is affecting the rate, we want to change its concentration, but we want to hold hydrogen's concentration constant. Okay, so between these two experiments, hydrogen was the same. We doubled the concentration of NO, and the rate did change. So certainly nitrogen monoxide is affecting the rate of that reaction. All right, so in terms of solving this, what you're really doing, the longhand way, is you're taking the rate law from, say, one of the experiments and you're dividing it by the rate law from the other experiment. But things are being held constant, like the rate constant, like the hydrogen concentration. So you can shortcut to the only thing that's affecting the rate, and for experiments 1 and 2, it's just NO. So let's look at those two. So experiments 1 and 2. I like to take the larger rate divided by the smaller rate. So I would take rate 2 divided by rate 1. Okay, and the only thing that's going to impact the rate is our concentration of NO, because the rate constant is a constant, hydrogen is being held constant. So this is just going to be NO from experiment 2, NO from experiment 1, raised to some power. Look familiar? Okay. And again, remember what we're really doing is we're taking the entire rate law for experiment 2 and the entire rate law from experiment 1, and we're dividing one by the other. But the rate constants are going to cancel out. The hydrogen concentration is going to cancel out. So we've taken the shortcut to here. Are we good with that? All right, so let's plug in some numbers. So we have So 5 divided by 1.3, is that almost 4? Okay. So sometimes, I think I did, yeah. Okay. So I just pulled this out of a book. If you're running this experiment in the lab, you don't expect your data to be perfect. You did a rate law experiment this semester in the 152 lab. If you took that, and you probably saw that it was supposed to be first order, and when you double the concentration, the rate was supposed to double, but it probably wasn't quite double. Anybody remember that experiment? Yeah? Okay. So what we would do in this situation, we'll give you better numbers on the final, but we would say that this is approximately 4. 3.8 is approximately 4. Okay? So x would equal to what? X would equal to 2. So now we know the exponent for NO. We need to then look at two different experiments for hydrogen. And which two experiments should we look at? 2 and 3. Okay, so 2 and 3, it's scrolled off the screen, but the first column was NO. So 2 and 3, we're holding NO constant. We are changing hydrogen, and the rate does change. Okay, so any change in rate here is only due to hydrogen in this case. So same calculation or similar calculation. I think rate 3 was larger than rate 2. So I think this was, see how my memory, see if it still works. Is that right? So this one looks like it's 2 is equal to 2 to the y. So y must be 1. Okay? So our rate law, let's go ahead and rewrite that. For NO, we found that it was second order with respect to NO. We just found out that it was first order with respect to H2. I'm sure you got yelled at enough in ALEX this semester telling you not to put exponents of 1. Yes? So I'm not going to write my exponent of 1 there, but it's understood. Okay? So this reaction would be what order overall? It'd be third order overall. So that's what the next thing, we know what it is meant by the order of reaction. We can speak of the order with respect to a reactant, and then the overall order for the reaction. So second order with respect to nitrogen monoxide, first order with respect to hydrogen, third order overall. Okay? Questions on that one? Make sure you understand the process. The process makes sense. You're just taking one rate law divided by the other one. But make sure you understand you only want to change one reactant and hold the other one constant. Yes,
so
Jennifer?
If you had like a follow-up question asking us to solve for K, would you just pick an experiment and plug in all those values?
And you read my mind.
Okay.
I was going to ask you the same question. Yeah, you might get a follow-up question to solve for the rate constant. And you said it just right. It doesn't matter which trial you choose because the rate constant is a constant for that reaction. Okay? So pick one of the trials, whether it's 1, 2, or 3, plug in the rate, plug in your concentrations, solve for K. Do we want to do that? Do we want to solve for a rate constant? No? All right. I think it's pretty straightforward, but just if we if we scroll up, using experiment 1, we would plug in those concentrations, plug in that rate, solve for the rate constant. Okay. We should probably talk, so I think that's a pretty easy calculation. Again, you could choose either trial. We should probably talk a little bit about the units of the rate constant. I don't know if I wrote that on the study guide. I don't think I did, and I probably should have. So what would the units look like for this reaction? So this one's third order. What would my units of K look like? Okay, so molarity squared seconds. Okay? So remember, the molarity term in the denominator, the exponent will be 1 less than the order. Okay, so this is a third order reaction. The molarity exponent will be a 2, 1 less than the order. Okay, so you could be, I can't remember if a problem like this is on the final, but you could just be given a rate constant, and then just by the units you would know the order of reaction, or you should know the order of reaction. Okay. All right, so that's the rate law, which tells us how concentration affects the rate. Okay, so this is the big focus. Although temperature is in there because temperature is in the rate constant and whatnot, the big thing out of this equation is if we change the concentration, how will the rate change? Now let's look at the integrated rate law. What does that tell us? So let me put up an integrated rate law here. Yes. Mm-hmm. Yes. So the integrated rate law tells us how concentration changes over time. Okay? So again, we're looking at a reactant, and so that reactant concentration is going to decrease over time. Okay? So we're with the integrated rate law, we can calculate this change in concentration over time. So it tells us a different thing. They're related, okay? Rate and change in concentration, but we get a little bit of different information from the integrated rate law. Which one is this? This is first order. This will be on the equation sheet, but it won't be labeled first order. Okay, you need to be able to look at that. And I think it's pretty easy. It has a natural log term in it. The other one you should know is that one. And that one is what order? This is second. We also briefly looked at the zero order one during the semester, but for the final, first and second, that should be fine. All right, next thing on here, know what to graph to determine if a reaction is first or second order. So there's our equations. These are the linear forms of those first and second order equations. So if we want to prove a reaction is first order, what should we plot? Okay, so our y value. So these are in a linear form, y equals mx plus b. I won't change that up on you. I will leave it in the proper linear form. So that's our y value. So y-axis, natural log of the concentration. What do we plot for our x values? Time. Okay. If it's first order, what should our graph look like? It should be linear with what slope? Negative slope, because this is a negative k. So if it's first order, we should get a straight line with a negative slope. The slope of that line will equal the negative of the rate constant. So that is one way we could figure out the rate constant for the reaction. There was one Alex problem like this, and I was helping a student this week with this problem, where you had to make these plots and then get the rate constant from the slope. Do you remember that one? Yeah. Some of you might still have that out there in your pie, just waiting for you. Okay. Look back in an old email for me if you have it, because I did send you an Excel spreadsheet that had the plots in it way back when, if you have to do that one. Second order. If we want to prove a reaction to be second order, what should we plot? 1 over the concentration versus time. If the reaction is second order, what should our plot look like? Yeah, straight line, positive slope. So it should be like that, or linear positive slope. Okay? Now, what you would see, if the reaction were first order, your first order plot would be linear, your second order plot would be a curve, if it's first order. Opposite to that, if it's second order, your second order one would be linear, your first order plot would be a curve. Okay, so only one of those will be linear for, assuming it's first or second order, only one of those would be linear. Yes?
On the final, would we have to make a graph ourselves?
No. No, you would not have to make a graph. You probably, easy question would be, this reaction is second order with respect to A and 0 order with respect to B. What would you plot to prove to prove the order of the reaction? And then you'd have to, one of the multiple choice options would be, a plot of 1 over concentration versus time or something like that. Other questions on this? Okay, you should also be able to do calculations with both of those equations. All right, so use either of those equations to solve for concentration at a later time or solve for time. Okay, and so let's rewrite those equations just so that we know them. I'm also going to write another form of the first order equation, which will be on the equation sheet as well. So those are the first order ones, and you know the second order one. Okay. So the typical problem might be you're given an initial concentration, you're given a time, what will the concentration be at this later time in the reaction, and you may or may not be given the rate constant. You could be given the half-life, so we should talk about that as well. So let me write the half-life equation up there. I do have that in the next bullet, but you might have to use the half-life to solve for K first. We just did this in class yesterday. Okay. But essentially, given everything on this side of the equation, solve for the concentration at a later time. Okay. Now watch for that natural log term. You will have, if you plug everything in here on the right, you will have the natural log of that concentration is equal to some number. Is everybody with me on that? So if we're solving for this concentration at a later time, we'll have the natural log is equal to some number. So how do we get rid of that natural log? E raised to that power. Okay, so watch for that. You'll probably see that. Okay. Now this other form of the first order equation I think is easier to use if you want to solve for time, because time is kind of isolated over here on the right hand side of the equation. But it's the same equation. And then this is the second order one. So if the reaction is second order and you need to solve for the concentration at a later time, that would be your concentration at a later time. Watch for that one because it's 1 over the concentration, so you're going to have to do the reciprocal or inverse at the end if you have a second order one. Okay? And then make sure you know the half-life for second order. You don't have to memorize this. So that will be on the equation sheet, but it won't come out and say, this is second order. Unless your exam starts talking to you, and then maybe you didn't get enough sleep the night before. I don't know. Who knows? Any questions on those? Question? No? Good? Okay. So yeah, the questions with these aren't terribly hard, but make sure that you plug things in the right place, and then make sure you know how to get rid of that natural log term if you need to, or if you have a second order, when you get to the end, you're going to have 1 over the concentration is equal to some number. You have to take the reciprocal at both sides. All right. We already talked about the half-life equations and maybe solving for the rate constant from those, so that's very common. So I bet you that's on the final, that you'll be given a half-life and have to solve for the rate constant first. So watch for that. Okay, next thing, know the definition of a catalyst. What is a catalyst? Okay, speeds up the reaction. By doing what? Okay. So the reason why it's a lower activation energy is it's a different pathway from reactant to product. All right, so a catalyst speeds up a reaction. Different mechanism, another way to describe it, pathway or mechanism from reactant to product that has a lower activation energy. Okay? The other thing that I didn't write there is the catalyst is not consumed in the reaction either. Okay? So that's what a catalyst is. Make sure it's kind of nice to know the typical energy profile. Something like this, reactants on the left, products on the right. Where would my activation energy be on this graph? That would be from here to here. So from reactant, I didn't get that quite in the right place. E sub A, activation energy. So from reactant up to the top. And what is the difference between reactant and product? That's our delta H. So at constant pressure, it's the difference in energy, but at constant pressure, which is typically what we're doing, that is the delta H. Okay? And so a catalyst, we're going to have the same reactant and product. It's just that our pathway from reactant to product will be different, and our activation barrier will be smaller. Okay. I thought I just lost one of my microphones, but I guess not. See if they're both still working. All right. I've done that before. You should hear me when I'm doing a recording for you guys and the batteries die in the middle of the recording and then I don't know it and I keep talking for like 20 minutes. Yeah, it's not pleasant to be around me when that happens. Because then I have to go back and record everything that yeah. And it's happened more than once. You think I would learn, but I just get going. I forget to look at the batteries, and they will die. All right. I was smart tonight, though. I did charge the batteries before I came here, so at least I thought I was being smart. We'll see. Okay. All right. Last couple of things for this chapter, and I think this is where we'll stop for tonight. This is a good stopping point. Get through the two oldest chapters. And then, what you might want to do is, before Sunday, look at the two practice finals and work all the thermo and all the kinetics material from those two practice finals. Okay, that would be a good idea. And then Sunday, we'll continue. We'll do equilibrium. We'll get back into acid-base stuff. You should be pretty familiar with all that stuff. So that might go pretty well for you. All right, Arrhenius equation. That is one form of the Arrhenius equation. That one is linear. The Arrhenius equation is actually a pretty cool equation because there's lots of stuff going on in that one equation. Okay? We have our rate constant, which is proportional to rate. So in effect, we have a relation to the rate of the reaction. We know the activation energy is going to affect the rate of our reaction. If it's smaller, the rate is faster. If it's larger, the rate will be slower. Temperature will certainly affect our rate. Most reactions will be faster as we raise the temperature. And then this term, which we don't do much with, has some cool things in it. It has collision frequency in there. It has orientation of collision. So there's a lot of factors that impact the rate of the reaction, and they're all in this equation. This particular one is linear. So one way we could determine the activation energy is by making a plot. Okay, now you will not have to make a plot on the final exam, but you should know what you should plot to figure out the activation energy. Okay, so what should you plot if you want to figure out the activation energy for a reaction? Y versus X, right? So natural log of K versus what? One over T. Okay? And assuming that we collect good data, what should that plot look like? Okay, it should be linear. And you'll notice there's a negative sign here, so it should have a negative slope. Okay? And what should that slope equal to? Okay? So that would be one way to figure out the activation energy for a reaction. You would measure the rate at various different temperatures. Okay, maybe 4 or 5 different temperatures. You would make this plot, best fit that straight line, and get the slope of the line. And then if we have the slope, R, what is R? That is the gas constant. This is energy. So the R with energy is 8.314 joules per mole Kelvin. Okay. So if we do this best fit, we'd have the slope. We know R is a constant. We would cross multiply here, solve for the activation energy. No, you have to memorize that. I'm sorry. Yeah. I'll actually give you 2 R's. That shows you how nice I am. You'll get that one, 8.314, and you'll get 0.0821. Wow. Bonus. What's that? Yeah. But remember, if it has energy in the equation, you're going to want to use the R that has units of energy. Okay? All right, there's one more Arrhenius equation you should know for the exam. So this is what we typically call the modified version of the Arrhenius equation, where we take 2 different rate constants, 2 different temperatures. Okay, so instead of having to plot, say, 5 different points, we hope our data is good, and we just take 2 points. So we take 2 different rate constants, we take 2 different temperatures, plug in R, and we solve for the activation energy. Okay. So this would be the type of problem where you're essentially giving 4 pieces of information. K1 and K2, T1 and T2, R as a constant, and then you just plug in and solve. Okay. Now, you might want to practice a couple of these because rearranging this equation can be a little problematic, just doing the algebra. Okay, so there will be some of these on the practice final. Okay, and it's the same R here. Since energy's in there, we want the 8.314. Oh, I'm sorry, I didn't see you. Mm-hmm. Yeah, there's different ways to write this. The book, so I'll probably change that. The book we were using for that last year was different, and they wrote it, if you put K1 over K2, then the negative sign goes away. So it's the same equation, it's just rearranged a little bit. All right, are we good with that? All right, last thing for tonight. Not the last thing for the final, but the last thing for tonight. Know how to determine if a proposed mechanism is valid. So again, this will be a multiple choice question. Most likely you will be given 5 proposed mechanisms, and you'll have to pick out the one that is valid. Sound familiar? It's coming back slowly. Oh, hey, it did do that for a while, though. That was pretty good. It kind of... I do have to clean off the hard drive. These videos I record during the semester take up a lot of space, and I usually wait till the end of the semester, and then I dump them to a external hard drive. All right. So there are 2 conditions that must be met for a proposed mechanism to be valid. What are those 2 conditions? Yes. Yes, there are 2 conditions. And they are? So remember, a proposed mechanism might have 2 elementary steps, 3 elementary steps. Those steps add up to what? Am I like speaking French up here or something? Yeah, basically. Acidically, actually, but, oh, that was really bad. I really didn't have lunch today, so I'm running on fumes. I had 2 breakfasts though, so I shouldn't complain. Best meal of the day, breakfast, right? All right, let's get done with this. All right. So you will have a couple of elementary steps. Depends on how complex the mechanism is. It might only be 2 steps. It could be 3. It could even be more. And those steps need to add up to what? Okay, they need to add up to the balanced equation. Oh, gosh. I actually write in cursive a lot, so sometimes my brain like glitches, and then I'll go from printing to cursive and not even realize it. Okay. So if you have a multiple choice problem, you can just look at the steps and add them together and make sure they add up to the balanced equation that's given in the problem. Okay? And what is the second condition? The rate law written from what? From what? Okay. Gosh. My brain has had enough today. Oh, I hate when I run out of room. It's kind of falling off the page. So the rate law written from the slow step, which is also called the rate determining step, must match what? Experimental. Okay. So your typical problem like this, it would say, the rate law was determined from experiment to be this. So you'll be given the experimental rate law in the problem. Here are the proposed mechanisms. Which one is valid? Okay. Now, I think checking step 2 first is faster. Find the ones where the slow step matches experimental first, and it might just be a couple of the 5 choices. And then you only have those, whichever ones match experimental, those are the only ones you have to add together to see if they add up to the balanced equation. Okay? There should be some of these. There are 2 practice finals posted. So there should be plenty of problems for your work. So again, now that I think this is the material you need to probably spend the most time on and start earlier with. And so I would think, sometime tomorrow, try to go through the thermo and kinetics material on both practice finals and see where you're at. Sunday we will meet same place at 5 o'clock, and we'll start with the equilibrium chapter. And then, we will meet again on Monday and then do the last stuff for the semester, which should be the freshest stuff in your memories. Okay? All right. Have a wonderful Friday evening. You are welcome. If you did not get your retest and you took the retest last night, they are down here, all finished up and graded. Yes?
Are they going to be up in the grade book, or are they already?
Well, so I'm hoping to get most of the grades updated tomorrow. At the latest, everything probably except SI points. Okay. So for SI attendance, they will not get those to me probably till Wednesday of next week. Okay. But everything should be up to date, certainly no later than Monday. But I'm going to try to get these exams up tomorrow, and then over the course of the weekend and into Monday, I'll try to make sure that all the attendance, pre-lecture quiz, Alex scores. Well, Alex, I can't really update till after Sunday night. Okay?
Thank you.
All right.
Somebody said thank you for doing this.
Oh, absolutely. Absolutely. Hope it helps.
Just have a question.
question on the exam. So I got like confused because it didn't come out to me to like the one that I wanted. Because it actually came out to be to 2.96, so we were supposed to round that to get to 3.0.
Yes. Yeah, so there were only 2 sig figs. So there's 2 sig figs here, 2 sig figs there. So these answers were just expressed to 2 sig figs. So 2.96 to 2 sig figs is 3.0.
Okay. I just got confused because I didn't like.
Yeah, this
see
is
what I
right.
was going for.
Yeah, that is right.
right. Yeah, that definitely sucks. Okay, I was just wondering.
Okay.
Thank you.
And then this one, fluoride.
Yeah, I was super bummed about that.
Because you have to do that.
And
See, I
then-
did. It was like just qualitative,
Yeah.
and then it was the same thing over here that you actually calculate.
No, that's okay. I was just, I don't know, my brain got reversed on that problem. Thank you.
So I actually had a quick question on, like, well, a couple, but for one for the test, one of the ones I got wrong was because I said that with the
Hold on just a
equivalence
second.
point.
Let me stop recording.
Okay.
this.